Large language models, or LLMs, have transformed how we interact with technology, from generating creative writing to solving complex problems. However, their rapid advancement has raised serious concerns about content traceability and potential misuse, such as spreading misinformation or violating copyrights. To tackle these issues, researchers have developed watermarking techniques, which embed hidden signals into the text generated by LLMs. This allows owners to trace the origin of the content and detect if it's been produced by their models. In this paper titled, Entropy-Guided Watermarking for LLMs, a test-time framework for robust and traceable text generation, authors Shizhan Cai from Nanyang Technological University, Liang Ding from the University of Sydney, and Dacheng Dao propose a new approach to improve both the quality of the generated text and the reliability of watermark detection. First, let's break down what watermarking involves. An LLM watermarking scheme has two main parts: embedding the watermark and detecting it later. Embedding can happen during the logits phase, where the model's output probabilities are adjusted, or during the sampling phase, where the actual tokens are selected from those probabilities. In logit-based watermarking, like the method by Kirschenbauer and colleagues, a hash function uses previous tokens to divide the vocabulary into a whitelist and a blacklist. The model then boosts the probabilities of tokens in the whitelist, making them more likely to be chosen. Detection involves statistical analysis to spot these patterns. On the other hand, sampling-based watermarking, as seen in works by Kuditapudi and Christ, integrates random keys directly into the token selection process. This helps preserve the original text distribution, meaning the output stays natural and aligned with what the model would produce without watermarking. Despite these advancements, existing methods struggle with a key trade-off. They often sacrifice text quality to ensure the watermark is detectable or vice versa. For instance, Kuditapudi's scheme measures the distance between the watermarked text and a secret key for detection, but it can lead to irregular outputs, especially in scenarios like few-shot prompts. Few-shot prompts are when the model is given a few examples to guide its response, such as starting with, "The best answer is." This can result in inconsistencies that degrade the user experience and might even reveal the watermark's presence. Similarly, Christ's method uses a score function for detection, but it falters against attacks like text modifications, where someone tries to alter the output to remove the watermark. These weaknesses make it hard to maintain both high text quality and robust detectability. To address this, the authors introduce a novel scheme that uses a cumulative watermark entropy threshold. Entropy, in this context, measures the uncertainty or randomness in the watermarking process. The idea is to monitor the entropy as the model generates text and only apply watermarking when it exceeds a certain threshold. Here's how it works. During text generation, the model starts by producing output without watermarking if the cumulative entropy is below the threshold. This keeps the initial text natural and high quality. Once the entropy surpasses the threshold, the system uses the preceding tokens as a seed to generate a secret key on the fly. This key then guides the watermarking for the subsequent text. This approach is flexible and compatible with existing sampling functions, meaning it can work with various LLMs without requiring major changes. It also adapts well to different scenarios, like few-shot prompts, by adjusting the threshold to align with user-defined templates. For example, if a prompt has a predictable structure, the threshold can prevent unnecessary watermarking that might disrupt it. The authors emphasize that this method balances two critical requirements: text quality and detectability. Text quality ensures the output remains coherent and useful, just like non-watermarked text, preserving the user's experience. Detectability means the watermark can still be reliably identified, even if the text is slightly modified. To evaluate their scheme, the researchers conducted experiments on multiple LLMs using popular datasets like Math and GSM-8K, which test mathematical reasoning. The results were impressive, with their method achieving over 80% improvements in performance compared to existing techniques. Specifically, it maintained high detection accuracy while minimizing any degradation in text quality. One key advantage is its ability to handle adversarial attacks. These are deliberate attempts to remove or obscure the watermark, such as paraphrasing or editing the text. The entropy-guided approach makes the watermark more robust because it's tied to the dynamic generation process rather than a fixed key. The paper also includes a figure illustrating the watermarking workflow. It shows how the secret key is implanted during sampling, represented by apricot arrows, while the original LLM generation flow is shown in blue. This visual helps clarify how the process integrates seamlessly into the model's operation. Overall, this framework advances the field by making watermarking more adaptable and effective. By releasing the code, the authors aim to encourage further research and real-world applications, potentially helping to safeguard LLMs against misuse while supporting their beneficial uses.